The instructions say, label each segment with its length. Use the square root symbol to express lengths that are not whole numbers. I want to start by looking at line segment I. Line segment I is a horizontal line segment. It goes straight left and right, and so it's really easy to find the length of line segment I. We can see that line segment I is 1, 2, 3 units long. So the length of line segment I, the length L, is 3 units. Now you can see that most of the line segments on this page are tilted line segments. They're not line segments that are strictly horizontal or strictly vertical. When that's the case, we can't just count how long the line segment is. We're going to have to use our knowledge of squares and square roots to help us. So for each of these tilted line segments, you're going to start by drawing a tilted square. I'm going to use segment D as an example. So I'm going to draw side lengths onto segment D to make a square. So there we have a square that uses line segment D. Now the reason for drawing the square is now I can find the area of the square. Remember, we've talked about how to deconstruct these tilted squares into other shapes. So I'm going to draw in some slope triangles to split up D into some shapes I can find the area of. I know the area of this little square here in the middle is just 1. I know that the area of this little triangle up here, I can do base times height, so 2 times 1 divided by 2 is also 1. So each of these triangles has an area of 1. All together, I've got 1, 2, 3, 4, 5. So the area of square D is 5 square units. That means, remember, that the side length is going to be the square root of 5. Remember, if you have the area of a square, you take the square root of the area to get the side length. So the side length, the length of segment D, is the square root of 5. Now, the square root of 5 is not a square root that we can do in our head. 5 is not a perfect square number, so the square root of 5 is not going to be a nice whole number. So we'll just leave the answer as the square root of 5. So for the rest of these tilted segments, you need to draw tilted squares, find their areas, and then take the square root of the area to find the exact side length of each tilted segment. The instructions for Part 3A say, estimate each non-whole number length to 1 decimal place. Then locate the lengths on a number line. If we look up at number 2, most of our segment lengths are non-whole numbers. The only whole number lengths we have are 3, 4, and 5. For all of these other side lengths, we have to figure out an estimate of each of those side lengths to 1 decimal place. I think I'll look at the square root of 13 as an example. So to figure out where to put the square root of 13 on the number line, and to figure out an estimate for the square root of 13 to 1 decimal place, I have to start by thinking about perfect square numbers that are close to 13. The perfect square number that is closest to 13 but less than 13 is 9. The perfect square number that's closest to 13 but more than 13 is 16. Now, we're not actually looking at the number 13, we're looking at the square root of 13. So I'm going to take the square root of 9 and the square root of 16. So what I know is that the square root of 13 is going to be somewhere in between the square root of 9 and the square root of 16. Now, the square root of 9, we know, is just 3. The square root of 16, we know, is just 4. So now we know that the square root of 13 is somewhere in between 3 and 4. So we know we're going to write the square root of 13 on the number line somewhere in between 3 and 4. But we want to estimate to 1 decimal place. So the next thing we have to think about is, what is the square root of 13 closer to? Is it closer to 3 or is it closer to 4? Well, if I look at 13, 13 is 4 away from 9. 13 is only 3 away from 16. Since 13 is closer to 16, the square root of 13 is going to be closer to 4. So now I know that the square root of 13 is somewhere between 3 and 4, but closer to 4. So to try and figure out the value of the square root of 13 to one decimal place, I'm going to start by just picking a decimal number between 3 and 4 that's closer to 4. And the first thing I think I'll try is the number 3.6. To see how good of an estimate 3.6 is of the square root of 13, I just need to multiply 3.6 by itself. This is work you could do by hand, or this is work you could do on a calculator. I'm going to grab a calculator and type in 3.6 times 3.6. And I get 12.96. 12.96. Now that's really close to 13. It's just a little bit smaller. Now to make sure that 3.6 is the best estimate, since 12.96 is a little smaller than 13, I might also try looking at 3.7. So if I multiply 3.7 by itself, you could do the multiplication by hand. I think I'll use a calculator. 3.7 times 3.7 is 13.69. Now 13.69 is 0.69 higher than 13. 12.96 is only 0.04 lower than 13. So that tells me that 3.6 is the better estimate for the square root of 13 than 3.7. Now I can place the square root of 13 on the number line. I can go to the number line until I think I get to about 3.6. Let's see, this is 3.5 or 3.5, so 3.6 is a little further up. So I could mark a point here at a little more than 3.5, and then I would label that point as the square root of 13. So as you continue to work on placing the rest of these numbers on the number line, I do want you to be trying this procedure that I modeled here, where you decide between which two consecutive whole numbers is that square root, which one is it closer to, estimate a value, try it out, see how it works, revise and refine if possible, and then place the result on the number line. You should not be using the square root key on your calculator at all. If you feel like you need to do some of this work on some scratch paper, that's totally fine. Just go ahead and attach it to your yellow page when you turn it in.